Section 6.3 Permutations and Combinations. Permutations. There are two ways of ordering two different objects A and B, AB, BA. So, the number of two permutations is 2. The number of permutations of n object is denoted by P of n. We find the ordering of such kind in 2 steps. Step 1, select the first object. Step 2, select the second object. There are 2 ways to do step 1, and after doing step 1, there is only one element left, so for step 2, we have only one possible outcome. The multiplication principle gives the answer. P of 2 is 2 factorial. To order 3 objects, A, B, C, we can figure out that there are only 6 such orderings, and we can obtain one of this ordering by performing these 3 steps. Select the first object. There are 3 ways to do this. Select then the second object. 2 elements are available now, so 2 outcomes. And step 3, select the third object, 1 outcome. And we get that P of 3 is 3 factorial. Similarly, we can prove that P of n is n factorial. Example: how many permutations of the letters A, B, C, D, E, F contain the substring D, E, F? The answer is not 6 factorial, because we want D, E, F to be in this order together. The answer is just 4 factorial. To figure this out, we take 4 tokens and write A, B, C on the first 3 and D, E, F on the 4th token. So we obtain all permutations that satisfy the requirement of the example by ordering those 4 tokens in all possible ways, and we know that we can do it in 4 factorial ways, which is P of 4. Definition: an R permutation of n distinct elements, x1 up to xn, is an ordering of R element subset of this set of n elements. The number of R permutations of n distinct elements is denoted by Pnr. So if R is equal to n, Pn is equal just to P of n, which is n factorial. Example: the 2 permutations of these 4 letters, A, B, C, D, are written here, and we see that they are all together 12 different 2 permutations of 4 objects. And 12 is 4 times 3. We can find a formula for P4n, P42 this way. Perform these 2 steps. In step 1, select the first letter to write. There are 4 letters available, so 4 outcomes here. Then perform step 2. Select the second letter to right. 3 letters are available now, so 3 possible outcomes. And the multiplication principle says the total number of 2 permutations of 4 objects will be 4 times 3, which is 12. Similarly, P of 5, 2 will be 5 times 4, 20. P of 5, 3 will be 5 times 4 times 3, which is 60. Because here we have to perform 3 steps to write the 3 permutations. In general, arguing similarly to this example, we can prove this theorem. If n is a positive integer and r is a positive integer less than or equal to n, then Pn is n times n minus 1 times n minus 2, and so on, times n minus r plus 1. Here we have a product of r consecutive decreasing integers starting from n. Example. In how many ways can we select a chairperson, vice chairperson, secretary, and treasurer from a group of 12 persons? The answer is the committees are 4 permutations because the positions are specified, the positions in the committee. So P12,4 is the answer, and P12,4 is 12 times 11 times 10 times 9. So we have 4 consecutive decreasing integers multiplied starting from 12, which is this number. Here, if we continue with multiplying this by a factorial up and down, in the numerator we'll have 12 factorial, in the denominator 8 factorial. And 8 factorial is just 12 minus 4 factorial. 8 is 12 minus 4. So similarly, we can see that P and R can be written in this form, n factorial over n minus r factorial. Problem. How many permutations of the letters from A to H contain the string ABC? Solution. ABC must occur in a block in this order, so we can select 1, 2, 3, 4, 5, 6 tokens, write ABC on the first token, and then D on the next token, and so on, H on the 6th token, and then order these tokens in all possible ways, which is 6 factorial. This is the number of all such strings. Problem. In how many ways can 5 distinct Martians and 8 distinct Jovians wait in a line if no 2 Martians stay together? Solution. An ordering of this kind can be done in 2 steps. Step 1, order the Jovians. There are 8 of them, so 8 factorial different permutations are possible. Then consider the positions before, between, and after Jovians. There are 9 possible positions to place a Martian, because no 2 Martians can stay together. So we have to order, we have to select 5 of those available 9 positions and order them. And there are P9, 5 such orderings. So the answer is given by the multiplication principle. We multiply the outcomes of step 1 and the number of outcomes of step 2 to get 8 factorial times P9 5 factorial, and the answer is this big number. Combinations. Definition. Let X be a set of n distinct elements and R be an integer between 0 and n. Any R element subset of X is called an R combination of X. The number of R combinations of X is denoted by CNR or n choose R. Example, if X is the set of the letters A, B, C, then one combination is one of these one element subsets. So C31 is 3, C32 is also 3. We have these two element subsets, and there is only one 3 element subset. The 0 element subset is the empty set, so C3 0 is 1. In order to obtain a formula, let's order the 2 combinations. It is this 2 element subsets. 2 letters can be ordered in 2 different ways, so obtain 6 orderings. And these are all 2 permutations of 3 letters. So we have the 2 factorial times C32 is equal to P32. From here we obtain a formula for C32. Just divide both sides by 2 factorial. Similarly, in general, we can obtain a formula for CNR by ordering any R combinations in all possible ways, and then solving the equation similarly like here. We'll get this result. CNR is PNR divided by R factorial. Just replace 3 with n, R with 2, here and here you get this. So we have a formula for CNR, which is this, and here in the numerator we'll get n factorial if we multiply up and down by n minus R factorial. So this formula can be written this way. CNR is n factorial divided by R factorial times n minus R factorial. Example. In how many ways can we select a committee of 3 of a group of 12 persons? Solution. Because they are not positions given in the committee, we have an ordered selection, so 3 combinations. The number of 3 combinations of 12 objects is C12-3, and we have a formula for that. When you perform computation by hand, it is more convenient to use this formula. If we use a calculator, there is a special function there to compute CNR. Corollary, let R be less than or equal to n, where n and R be non-negative integers, then CNR is equal to C and n minus R. One possible way of proving this is to use the formula from the previous theorem and evaluate and simplify the left-hand side and the right-hand side. We'll end up with the same expression. Here we'll present a combinatorial proof. Suppose that S is a set with n elements. If A is a subset of S and A has R elements, then A bar will have S, this is just the difference between S and A, so it will have n minus R elements, and vice versa. So there is a bijection between the R element subsets of S and the n minus R element subsets of S. This bijection shows that the number of R element subset is equal to the number of n minus R element subsets. That is, we have this equality. Problem. A club consists of 6 distinct men and 7 distinct women. In how many ways can we select a committee of 3 men and 4 women? Such a committee is an unordered selection because we don't have positions given in the committee. We can select a committee of this kind, the kind described in a problem, in 2 steps. Step 1, select 3 men. There are 6 men available, an ordered selection of 3, so it is 6, 3, apply the formula, you get 20 outcomes. After that, perform step 2, select 4 women. There are 7 available, an ordered selection, the number of outcomes is 7 choose 4, which is 35, just apply the formula from the theorem. And then the multiplication principle applies. We multiply the outcomes of step 1 and step 2 to get the answer, 700 committees.